this presentation on the equations of state. Give you some idea of how we get some of the values that we use when we're looking at tables. The way this fits into the greater context of this class is right here. So we're after refrigeration systems, and we're now looking at the thermodynamic relations briefly today before we get into ideal gas mixtures. All right, so we're familiar with getting information. So pressure, specific volume, temperature. We get that on tables, right? We have pressure, we have temperature, we can get specific volume. And with those, we can also obviously see we could get internal energy, enthalpy, and entropy, right? And we could maybe use two of those to get the other ones. But we have all this information in very much in the table aspect of it. We can also get this graphically from our compressibility chart. So here's Z. And what happens here is we have PVRT, and we have our reduced pressure we can calculate down here. And we find that on our reduced temperature curve. And then we can calculate what our Z value is, and then back calc out specific volume if we know our pressure and temperature, or temperature if we know pressure and specific volume. And so we've done that graphically. What we're going to talk about today is analytically, how can we find this PV-T relationship? But where does that come from? And this is the virial equation of state. So you can see where the compressibility shows up here. Just this part right here gives us the is what's kind of used to get the graphical piece using ideal gas. So when Z equals 1, we get ideal gas, and we'll come back to that. But each one of these extra terms deals with interactions between molecules. So the second term looks at interactions between two molecules. The third term considers molecules or interactions between 3 molecules, and then between 4 molecules, et cetera, et cetera, et cetera. And so this gets really complex. So simplicity is very important in calculation time and computation time if it ends up being something you program into a computer. So here's another version of it using specific volume rather than pressure. But again, each term represents the same thing with no interactions, 2-particle interactions, 3-particle interactions, etc. So let's focus on this first piece here, ideal gas, that we're familiar with. All right. So when Z equals 1, we know that we get the ideal gas equation, PV, specific volume, equals RT. And there's several assumptions that are made when we use the ideal gas equation state. All the molecules are identical, they're all the same, and molecules are tiny compared to their average separation. We would look at them as point masses, and we're going to come back to this in a little bit. All right, molecules do not interact with each other, right? Another big assumption we make here with ideal gas. The molecules obey Newton's law of motion, and their motion is random. Collisions between the molecules and the container are elastic, completely elastic. All right. So we looked at all those things, and what we're going to see here is that's really not the case, and hopefully you remember this from chemistry class. Well, if we look at the separation distance that we have between two molecules, and this is where they're actually touching versus here where they're really, really, really far away from each other. When they get really close, the repulsion's dominant, right? They actually want to push each other away. So kind of an interesting way to look at it, but this is like a dating relationship, right? When you're far enough away, you get within a certain distance, there's a lot of attraction, right? A lot of attraction when you get close enough. From a distance, there is still some attraction, but not much. But when you get closer and you get to see the person you're eyeing, checking out, right? There's a really strong attraction. But then when you get too close, too soon especially, there's a little bit of repulsion that happens, and it actually is exponential, all right? So this is what actually happens between two molecules. When they get really close, there's repulsion. There's an attraction when they get further away, and actually a very strong attraction before it drops off as you get further and further away from two molecules. But there's still an attraction. The ideal gas, because of point masses and because of ignoring interactions between molecules, remember, it only has that first term from the virial equation of state. It doesn't have that B term, C, D. It just has that one. So it's just looking at the general motion of particles, not the interaction between them. So that's the difficulty that the ideal gas equation had. Van der Waals came along in 1873. He said, hey, let's include some of that information. Let's include those values. And so when we have this new equation, you can see there's a lot of similarities. We got pressure, we got specific, it was universal gas constant, we got temperature, we got specific volume down here. But now we have this A, or the B, and the A. Maybe I should have changed color of my pen there, but you can get the idea there. Those are both positive constants. They'll always be positive. And there's something we can look up, and I'll show you where those come from. But this value here, so the second term here, accounts for forces of attraction between molecules, so it captures that piece. And B accounts for the finite volume occupied by the molecule. So the two things I pointed out with the ideal gas is that there was no attraction, and we said there were point masses. So both those aspects are now included in some regard with the Van der Waals equation here. So physically meaningful values of the specific volume are always real, positive, and greater than B. All right, so they have to have some initial value there. It's meaningful. All right, and again, let's give a little bit more details there. All right, so this is where those A and B come from. So using this equation, our Van der Waals equation, so that's one equation. We're going to solve three equations here. So this is the first one. We get some other equations here. If we look at these isotherms, and we look at the change in pressure with respect to specific volume along that isobar, and we look specifically at the critical point, where that slope is equal to 0. That's what we're going to solve for. And if we take the partial derivative of our Van der Waals equation, which is in terms of pressure, take the partial derivative with respect to the specific volume, we're going to come up with some equation. Now that'll be our first equation, and we do it again, and we take again our Van der Waals equation, we take the second derivative with respect to the specific volume, and we have our third equation. So the first equation is Van der Waals. The second equation is the first derivative of the Van der Waals equation. The third equation is the second derivative of the Van der Waals equation. And we use all those together, and we can solve for our A, our B, and the specific volume, the critical specific volume at that critical point there. What that all leads to is this. All right, here's a really neat comparison. Oops, went too fast there. Here's a really neat comparison between the ideal gas and the Van der Waals equation. Right. So here we got pressure, we got volume, we got temperature. So same thing over on the Van der Waals plot as well. All right, we can see this nice little curve here. That's all well and good. But sliding ahead, check out this right here. Does that look familiar? That's the vapor dome. All right, Van der Waals equation just added one term. Right, now, obviously with the A and B terms, but really only two terms that subtracted from kind of our original ideal gas equation. But with that little bit more of information, we can capture the vapor dome. Now, that's pretty impressive. So a great improvement on the ideal gas equation. But it does add some complexity. So if you don't need that, and ideal gas gives you enough information, ideal gas is the way to go. Redlich-Kwong came along in 1949 and improved upon Van der Waals equations. Again, you see the same structure here. Actually, this is the same, looks like pretty much the same as the first term in Van der Waals equation, and a little bit more complexity here in the second term. All right, this is the best of the two constant equation of states. So there's some other models of these, but these are the main ones, Van der Waals and Redlich-Kwong, but this is considered the best of the two constant, A and B being those two constants, equations of states. Has better accuracy than the Van der Waals equation, and the evaluation A and B is similar, looking at the derivatives that occur at the critical point, just like the Van der Waals equation. Again, both these values here, as well as the Van der Waals equation values, they're found in our book is table A24, so you can look those up for different gases. Right. So those were just two constant equation of states. And again, they just had that first term, thinking back to the virial equation of state, Z equals, right? Thinking back to the virial equation, it was Z equals 1 plus our B value. So we have B as a function of temperature times our pressure. And so this term here accounted for the interaction between two particles. And so if we can add on to that, obviously we get more information about what's actually going on. So the Beatty-Bridgman is a multi-constant equation of state. So you can see we got our first term here, all right, just the ideal gas, and then you got 1, 2, 3 more added onto it, and that's more information there on what beta, gamma, and delta are. So getting much more complex, but again, taking in more information of interaction between not just 2 particles, 3 particles, 4 particles. All right, a lot of extra information there. The Benedict-Webb-Rubin, even more complex, a lot more information there. And that's all well and good. So what is this? What is the value of these equations? Where are we going to see these? Where are we going to end up using these? Again, the more simplistic you can use and still get the information, the accuracy that you need, go with the simple. But if you need the complexity, you want to use that as well. So let me show you really quick where that shows up. All right, here's the development of the equations of state for R134A. So I'm going to show you how that's used. So there's a slight difference if you've looked at the table values, a slight difference between the table values of R134A in our book and the values that EES produces. I think people have seen that before. Students have mentioned that in class. And here's why. The 1988 paper is the equation that our book uses. So here's the abstract from that paper. So thermodynamic properties of a new stratospherically safe working fluid refrigerant 134A. So this is the development of trying to create refrigerants that were better for the environment than previous ones. All right, and so you can see down here, in addition, the thermodynamic data are correlated to the equation of state from which enthalpies, entropies can be calculated. So that's the beauty of this equation of state. For the reading that you do when you check out the handout, and I think, yeah, it's also in the study guide. When you do the reading in the book, you'll see how we can actually use this equation of state to calculate enthalpies, entropies, specific internal energies. All right, and then you can see the sentence right after that, using appropriate algorithms, a Fortran computer package has been developed to generate the tables. All right, so that's where we got our stuff from. So I want to look at these other papers here. All right, and my links do work, so you don't have to worry about that statement. All right, let's first look at this 1992 paper by some NIST guy. All right, so here's that paper. So thermodynamic properties of R134A, and this is Marcia Huber and Mark McLinden. And if we read down here, the thermodynamic surface of R134A is expressed in terms of a 32-term modified Benedict-Webb-Rubin equation of state. All right, so they ran these experiments and they wanted to capture this all in this equation. So they ran some and got the basics of what they needed and developed this 32-term Benedict-Webb-Rubin equation of state. And that's what they used to kind of capture that information and then develop the tables that we get this information from. All right, so there's the 1992 paper. There's a 1994 paper, which I'll show you next. That has the equation that ES and Chengel, the author of our fluids book, I believe that his book is using, his thermo book, is using this equation. So looking at the background section, the equation of state presented in the paper were recommended as an international standard for thermodynamic properties. All right, so this is what the whole international standard should be. And so this is that paper right here. So an international standard. Oh, I'll keep sliding ahead. Sorry about that. All right, an international standard formulation for 134A. And you can see down here, well, they don't actually name if it's a Benedict-Webb-Rubin. They do fundamental equation of state and the values of its 21 coefficients. All right, again, very complex. All right, and this is done by Rainer Tillner-Roth and Hans Dieter Bacher. I'm not good at German, so I might have butchered that. Finally, here's DuPont. DuPont's the one that actually makes the R134A, and here's their paper, all right, on it. And so here's the first couple pages, and I'm going to scroll down here and show you something here. On page 3, check this out. Equations. The modified Benedict-Webb-Rubin equation of state was used to calculate the tables of thermodynamic properties. It was chosen as the preferred equation of state because it provided the most accurate fit of the thermodynamic data over the entire range of temperatures and pressures presented in these tables. The data fit and calculation of constants for R134A performed for DuPont at the National Institute of Standards and Technology. We just looked at the paper under the supervision of Mark McLinden. All right, so he fed into this process, and so DuPont said, this is what we're going to use. And we're using the stuff that Mark O. McLinden did at NIST. All right, so it's kind of fun when you can follow the papers and see where things kind of loop back around to what people are doing. All right, again, over here you can see these talks about these tables and based on the modified Benedict-Webb-Rubin equation of state. All right, so again, just to give you an idea of how these equations of state are used. All right, so the example that we'll look at in the separate presentation, here's water vapor. Looking at water vapor pressure, 200 megapascals, sorry, I keep saying 220 megapascals and 400 degrees C. And we want to determine the specific volume, meters cubed per kilogram, using steam tables. We'll do it with a compressibility chart, which I'll show you, which is obviously on the next slide. Using the van der Waals equation, we're going to do it by hand, and then we'll do both van der Waals and the Redlich-Kwong equation in the EES because it can do iteration for us. So I'm going to show you by hand how to do van der Waals, do that iteration process. And then the ideal gas equation of state, and then we're going to compare all 5 of these, the steam tables being the standard of which we'll compare to. All right, so look for that in the example in a separate presentation. All right, thanks guys.